whenever you start a new chapter, it's picture time. So what does this picture have to do with exponential and logarithmic functions? Well, you have to read the little preamble here, right? So in this chapter we study exponential. These are functions like f of x equals 2 to the x. That was our first example, wasn't it? Where the independent variable is in the exponent, right? So it's not a polynomial. Polynomials don't have a variable up there. So exponential functions are used in modeling many real-world problems, such as the growth of a population. That's why it's picture time with people. It's the growth of a population, the growth of an investment that earns compound interest, the decay of a radioactive substance. That's another one. Once the exponential model has been obtained, we can use the model to predict the size of a population. What's this model that they keep talking about? Well, yeah, I mean, you use the exponential growth model to predict the growth of a population, so you can see historically over time what is the growth rate. You can just compute that by doing a census over a period of years, and then use that to predict into the future what that will be. Things get complicated by things like, plagues, mass migration. But yeah, you do what you can. So the inverse functions of exponential functions are logarithmic functions. So we'll be getting there soon enough. With exponential models and logarithmic functions, we can answer questions such as these. When will my city be as crowded as the city street pictured here? Really? I don't know, that would be tough to answer. I mean, maybe that's just a rock concert and they're all congregated in one place. When will my bank account have $1 million? Okay, I'm interested in that. When will radiation from a radioactive spill decay to a safe level? Yeah, like Treasure Island, anybody? Follow the news? Yeah. Treasure Island is like the Bay Bridge, goes from San Francisco to Oakland, I think. And there's a little island in the middle there where the bridge connects. You can get, there's an off-ramp. You can visit Treasure Island. In fact, they've been trying to build it up as a residency location. Unfortunately, it was used to store radioactive waste, apparently, so, oh well. So, in the focus of on modeling at the end of the chapter, we learned how to fit exponential functions to power curves and data. Really? Oh, okay, so we'll have to see about that if there's time. I guess I want to be over here if I'm going to use the page thing. Okay. So, okay. So we've seen some of this already. We saw a to the x. Notice that their nomenclature is a little different than mine. I don't know if you can read that. It's a little small, isn't it? Yeah, a to the x. So I wrote a times b to the x, because I tend to think of b as a good name for base. And they don't have a scaling factor there, right? But, if the scaling factor is 1, that's sort of the standard scaling factor. So they just got a scaling factor of 1, and they're calling the base A rather than what I did, call it B. So calculators, yeah. So that's part of why I wanted to get out the the computer, is so I have access to the calculator. For instance, what were we computing here? What was it, 9/5 to the 1/4 power? How do you do that with a calculator? Well, first you have to get out your calculator. So, not the calculator. Calculator.
I'm sure the school removed calculators.
They do what?
Like in the tutoring center of retail. Like they're all removed.
They're disabled?
I guess. Yeah.
Install that? Okay, get. It's working. Sign in with Microsoft. No thanks. Okay. Couldn't install. Couldn't. We'll retry shortly. Really?
Just go on Google and use the calculator.
Yeah,
I'm just kind of shocked. Why would they disable the calculator? I've never heard of that.
Go to see details real quick. I'm curious.
that blue link.
Yeah, so I mean, yeah, you can just use Google. Okay, so,
Or not.
We just go to the to the 1/4 power. We need the parentheses there, right? Oh, 1/3, 1/4. Yeah, and there. Do we say 1.158?
Yes.
Yeah. So I guess that's an okay to do. I mean, I prefer the regular calculator because you get like memory buttons and you can see your history and that sort of thing. It was somebody's request. That's a movie coming on. Okay, so, and the other thing is that you will want to have a scientific calculator to do sort of some computations. I know the last chapter we didn't use calculators, but so different calculators, so you want to get comfortable with some kind of calculator, and you'll want a scientific calculator. You can get one for $1 at the dollar store. Is that the dollar store calculator? Great. Yeah. Does it work properly? Okay. Because sometimes they're gimpy, right? The quality control is. That's why they cost $1, because every fourth one doesn't work properly. So, but yeah, if you've tried it out for a while, then it's probably good. So yeah, notice that a scientific calculator will typically have parentheses, right? So if you're doing 3 to the negative 2/3, you'd say 3, here comes an exponent. That's usually a little caret sign like this, but sometimes it's an x to the y button. So a lot of calculators, instead of a caret, will have a little x to the y thing. So here comes an exponent, right? And if you want the exponent to do some sort of calculation before you apply it to your base, you should use parentheses, right? I think that's what I did up, well, it's not there. So then this is the negation key. So sometimes you need to say 2 and then negate it, depending on your calculator. So that's why I say, get accustomed to how your calculator works so you can get good results without doing things by hand. So, yeah, so let's then get out GeoGebra and do some experiments with GeoGebra. Okay, so it's here. No, here. Okay. So if I enter in the bottom here, can you see? Yeah, it's a little small, but this is the input line down here. And I'm going to say, I want a function of the form a times b to the x power. Should we add a c in there? What if we added c? Okay, then it says, so if you name your parameters a, b, and c, say, and it says, do you want to create sliders for those? And yeah, I do. It'll give you default values for your sliders, but we can change those. So for instance, C ranges from -5 to 5, and what does that do? Well, it's just shifting the graph up and down, right? That's a vertical shift. And A is 1, B is 1. Can B be 1?
No.
Yeah, that was one of the things we disallowed, right? And you can see why, right? If b is 1, then you just get a constant function. That's not exponential. We don't consider that to be exponential. So what if b is bigger than 1? Well, then it's going to be a growth function like that. If b is less than 1, then it's going to be a decay function like that. And it will decay towards the horizontal asymptote, right? So we can just shift that up. This is just a vertical shift. It looks like it's kind of going to the left as well, but it's just going up and down. A is a scaling factor, so if A is negative, it'll flip it upside down. A is positive and large, it's just going to stretch away from the axis. It doesn't look like it's stretching away on the bottom. That's because we've got a shift and a stretch. And the shift is down 0.85. What that does is fix the horizontal asymptote at -0.85, right? Um, So it's stretching away and then shifting, right? I guess that's the way to think about it, right? So if I move my shift to 0, oh, 0 is, where is 0? Okay, there's a 0 shift. Then you can see it's stretching upwards from the x-axis, factor of 5. If you make it negative, it'll stretch downwards, but it's still asymptotic to the x-axis, right? Okay, and what happens if the base is negative? You don't get any graph, right? What if the base is 0? What do you get? Well, not all of the x-axis, right? It's hard to tell on here. But if you look very carefully, you see that this is slightly green. That's the color of our curve. If we make the curve a different color, maybe make it thicker. So I can say, yeah, object properties. Yeah, how about the color? Let's make it blue. I don't know, the style, let's make it thicker. There, okay. So that makes it more obvious that, yeah, it doesn't, so if b is 0, then 0 raised to a negative power is not a good value, right? But b raised to a positive power will give you 0. So that's an interesting special case. Okay, how are we doing? We should move on to some exercises. So the compound interest, so here's various exponential functions, all with a scaling factor of 1, which means they all have the same y-intercept at 1. You can see negative and positive scaling factors, bases. They're not negative and positive bases. They're bases bigger than 1 give you growth. So if the base is 10, you see that it's growing much faster over here, but it's also smaller on this side, right? So it's a much more extreme kind of growth. If the base is 2, then you get something much more gentle, although that's also exponentially growing. Okay, so that's a family of exponential. That's mama function and papa function. So we've got, identifying transformations. So what we know about transformations is shifting and stretching, right? And reflecting, I guess. So here's an interesting business here, comparing polynomial and exponential functions. So an exponential function will always grow faster in the long run than polynomial function. So here's a puny little square function, right? That's not going to grow very fast. Although for small values of x, it looks like the polynomial is growing faster. In fact, eventually the exponential will catch up and surpass and grow much faster than the polynomial. Even if it's a polynomial of degree 100, eventually the exponential will grow much faster. What else we got here? Compound interest, right? So there's this formula we were just talking about, where P is the principal, that's the initial investment. You can think of that as A naught. That would be another good name for P here. It's A of 0, right? When T is 0, this whole thing is 1, because it's raised to the 0 power, and you got P times 1. So R is the interest rate per year, N is the number of times interest is compounded per year, and T is the number of years. So I don't know, we could look at the exercises here. Yeah, so they give you some different examples of so this is compounding once per year, N is 1, so you got a 12% interest rate compounded once per year. That will grow in 3 years, $1,000 will grow to $1,404.93. So if you compound twice a year, you get a little more, right? Your interest rate per compounding period is only 6%, but you have more compounding periods, right? 6 instead of 3. So ultimately, that gives you a larger amount, right? So what if you compound daily? Well, it doesn't give you that much more, right? So compounding monthly, you'll grow $1,000 to $1,430.77. Compounding daily is actually less than $3 more than that, right? So it's a pretty small difference. And so the question becomes, what happens if you have instantaneous compounding? That is, the instant you gain interest, it goes back into the principal. And that's in section 2, that's called natural growth. But we have some exercises here which may be of some interest, but let me show you the ones that are on Mildly Math, and then we'll take a short break. MildlyMath.com. Click here, sign in. Keep saying read the message. Exponential functions, yeah. So here, basically saying what we said before. So it's just